So in this lecture, we want to look at more quantitative calculations for chemical equations. We learned how to write a chemical equation, we learned how to balance it, and I showed you earlier that the balancing coefficients represent the molar ratio in which the reactants need to be mixed, and the ratio which gives us also the amount of product that's going to be produced. So we're gonna use the balanced chemical equation, and we're actually going to learn how to calculate the amount of reactant that's required for a specific reaction. We're gonna learn how to calculate the amount of product that's gonna be produced. Now, why this type of calculations are important is because the scale in which you do your calculations is extremely important. So knowing what chemicals to use is important. That's why we write chemical equations, to see what products are going to be produced. But when you actually go into the chemistry lab to perform your experiment, you have to have a good idea of how much of each reactant you're going to need. Why is this important? For many reasons. First of all, we want our chemistry to be green. We don't want to use too much chemicals and then have it go to waste. So you want to use exactly the amount that you need. So if I need only 0.1 gram of a substance, then I'm not gonna scale up my reaction to get 100 grams of that substance and then dispose of the rest of it. So part of it is being green. Part of it is knowing exactly what you're working with. If you go to the chemistry lab in our campus, as you see, our glasswares are small. We don't even have the ability or proper glassware to do reactions in a very big scale. So knowing exactly how much of each substance to use is extremely important. That gives us ability to have control on our reactions. So we're gonna start by seeing how we can find out the amount of reactants and products in a balanced chemical equation. And towards the end, we also talk about what if our reactants are not in a proper mole-to-mole ratio that we're after. So we're gonna start by showing you balanced chemical equations. You're gonna learn a new word, stoichiometry, that basically represents the molar ratio in between the reactants and products. Then we're gonna start with very, very simple calculations. First mole to mole, and then once we feel comfortable with mole to mole, we expand it to mole to mass. And then the most complicated one is going to be mass to mass calculations. We show you how to do that. And then at the end of this lecture, we talk about limiting reactants. That's when our reactants don't have the proper molar ratio, and we talk about percent yield of chemical reactions, which is a very important aspect of an experiment. It tells us how efficient our experiment was. So let's do a little review of the concepts that we need to know for doing calculations or stoichiometry. So since it's all related to moles, obviously it's very important that you know how to convert to moles. Remember that there are two ways that you can convert to mole. If the mass is given to you, you're going to use the molar mass to convert to moles. And also, if the number of atoms are given to you, you can use Avogadro's number to convert to moles. So two ways to convert to moles, and having moles is going to be essential for our calculations. So if the mass of a substance is given to you, you use the molar mass to convert that to moles, and if the number of atoms, molecules, ions are given to you, you use Avogadro's number to convert those to moles. Now, as I said, this number of moles, we're going to put it together with the balanced chemical equations. and we're going to look at the stoichiometry of reaction. So stoichiometry represents the molar ratio in between the reactants and products. So let's look at this reaction. A reacts with B, that gives you C and D. Now, the balancing coefficients represent the molar ratio in between the reactant and product. So we're gonna do practice problems here, and we'll show you how you can use the balancing coefficients in order to find quantities of reactants and products in a chemical reaction. So let's look at an example. So you're looking at a combination reaction for the synthesis of water. So hydrogen gas reacts with oxygen gas, and from that reaction, water is produced. So this reaction is balanced. So you always gotta make sure that your reaction is balanced. And now what we wanna show you is that the balancing coefficients represent the molar ratio in between the reactants and products. So what does that mean? It means that when I look at this reaction here, the synthesis of water, what this tells me is that 2 moles of H2 gas reacts with 1 mole of O2, exactly 1 mole of O2, and from that reaction, exactly 2 moles of H2O is going to be produced. So I'm using these balancing coefficients as molar ratios in between reactants and products. And also keep in mind that the balancing coefficients represent only the molar ratio. Now, these balancing coefficients, or our molar ratios, could be used as conversion factors. So just focusing on the balancing coefficients, I could write a conversion factor between hydrogen and oxygen, for example. So based on the balanced reaction, each 2 moles of hydrogen reacts with exactly 1 mole of oxygen. Or you can say each 1 mole of oxygen reacts with exactly 2 moles of hydrogen gas. So you can write these conversion factors for any 2 components of your chemical reaction. So it could be in between the reactants, it could be in between the products, or you could use a reactant and a product. So here we show you all possible conversion factors or mole-to-mole ratios that you could use. So for example, based on the balanced reaction, I can look at the ratio in between H2 and H2O. So based on the balanced reaction, each 2 moles of H2 produces exactly 2 moles of H2O. Or I could write this as each 2 moles of H2O is produced by the reaction of 2 moles of hydrogen gas. So all different possibilities here. I could also look at the ratio in between oxygen and water here. So based on the balanced reaction, each 1 mole of oxygen gas produces 2 moles of water, or each 2 moles of water is produced by 1 mole of oxygen gas. So again, keep in mind that to do any sort of quantitative calculations, we have to look at the balanced chemical equation. And also keep in mind that the balancing coefficients represent molar ratios. That's extremely important. So balancing coefficients represent molar ratios, and we can write the molar ratios as our conversion factor to figure out exactly how much of reactant and products we're gonna need for our experiments. So let's look at a couple of examples here. So you're looking at a reaction of hydrogen gas and oxygen gas, which is a combination reaction, and that gives you water. So the balanced chemical equation is given to you. So based on the balanced chemical equation, we know that if we have 2 moles of H2 and 1 mole of O2, we get 2 moles of H2O. But what if for a reaction we don't want to use 2 moles of H2? Then what do we do? So here is an example. You start with 4 moles of oxygen and you want to know how many moles of water can be produced. So basically from moles of oxygen, you want to find moles of H2O. So from moles of O2, you want to find moles of H2O. Now from mole of one compound, which is O2, I want to convert to a different compound, H2O. Remember that whenever you go from one compound to a different type, you have to use the mole-to-mole ratio. There is no other way of converting in between two different compounds. So starting with 4 moles of O2, based on the balanced reaction, each 1 mole of oxygen produces 2 moles of H2O. You set it up in a way that mole and mole of oxygen cancel out, and you end up with number of moles of H2O. So we use balancing coefficients as molar ratios, and those molar ratios were used as conversion factors to go from the number of moles of oxygen to number of moles of H2O that would be produced. So let's look at another example. You're given this balanced chemical equation. Carbon dioxide gas reacts with hydrogen gas. From that reaction, methane, CH4, and water is formed. So part A is asking you to find the number of moles of H2O that would be produced from the reaction of 3 moles of carbon dioxide. So from moles of carbon dioxide, you're going to moles of H2O. So here, from moles of carbon dioxide, you want to find moles of H2O. So in order to go from moles of carbon dioxide to moles of H2O, you look at the balance equation and you use the balancing coefficients in between carbon dioxide and H2O. So you start with 3 moles of carbon dioxide. Based on the balanced reaction, each 2 moles of water is produced from a reaction of 1 mole of carbon dioxide. Now, moles of carbon dioxide and moles of carbon dioxide cancel out. You end up with moles of water. Now let's look at part B. You want to find the moles of H2 hydrogen gas that's needed to produce 3 moles of H2O. So from moles of H2O now, we want to find moles of H2. So what's given to you is 3 moles of H2O. What we're looking for is the moles of hydrogen gas. So we look at the balance equation. The mole-to-mole ratio between hydrogen gas and H2O is 4:2. So for each moles of hydrogen gas, you would expect 2 moles of water to be produced. So moles of water cancel out and you end up exactly with 6 moles of H2. So let's look at this flow chart here. Remember that from the balance equation, you can find the mole to mole ratio. So if moles of one compound, either reactant products are given to you, you can use the balancing coefficients as the molar ratio to find the moles of the desired compound. So with balancing coefficients, you can only work with moles. So in order to use balancing coefficients, you have to have moles. Now, if the moles are not given to you, the moles of known compound is not given to you and you're given the grams, remember that you have to convert from grams to moles first using the molar mass. And once you convert to moles, then you can use the balancing coefficient. And also, if the moles are not given to you and the number of atoms, molecules, ions are given to you, you still need to convert to moles. And in order to convert to moles, you're gonna have to use Avogadro's number to convert to moles. So once you have the moles, you use the balancing coefficients as your molar ratios. And again, keep in mind that you will end up with the moles of the desired compound. Now, if the question is asking you for the mass, from there you do one extra step, use the molar mass, convert it to grams. If you're asking you for the number of moles, after you have if we ask you for the number of atoms, molecules, ions, you use Avogadro's number to convert the number of moles to the number of atoms. So let's do examples and see how we actually use this information. So you're looking at a combustion reaction here, and you want to know how many moles of carbon dioxide will be produced by reaction of 2 moles of glucose. So the combustion reaction of glucose is given to you. And you want to know if you have 2 moles of glucose, so from moles of glucose, which is C6H12O6, you want to find the moles of carbon dioxide. So the type of conversion I'm doing is mole to mole. So mole is given to me, and I'm also solving for moles. So in that case, we can just write the molar ratio in between glucose and carbon dioxide to solve this. Now, based on the balance reaction, each mole of glucose produces 6 moles of carbon dioxide. Or I could say each 6 moles of carbon dioxide are produced from a reaction of 1 mole of glucose with enough oxygen, obviously. So these are the 2 possible conversion factors that I could use. Now, starting with what's given to me, which is the moles of glucose. So we have 2 moles of glucose. I want to choose the conversion factor in which moles of glucose cancel out, and I want to end up with only moles of carbon dioxide. So I'm going to use the second one. So each 6 moles of carbon dioxide is produced from the reaction of 1 mole of glucose. And from here, moles of glucose cancel out. So from the reaction of 2 moles of glucose, you'll get exactly 12 moles of carbon dioxide. So let's do another example here. So you're looking at a combination reaction of hydrogen gas and oxygen gas that produces H2O. How many H2O molecules are produced when 0.010 moles of oxygen react based on this balanced equation? So let's see what's given to us and what we're solving for. So moles of oxygen is given to us. And from moles of oxygen, we want to solve number of H2O molecules. So we can't go directly from moles of oxygen to the number of H2O molecules. In order to find the number of molecules of H2O, you have to have the moles of H2O. So our solution map should be from moles of O2. First, we're going to find moles of H2O. And once we have moles of H2O, we're going to find the number of H2O molecules. So we have 0.010 moles of O2. To find the number of moles of H2O, we use the balancing coefficients as our conversion factors. So each mole O2 produces 2 moles of H2O. So moles of O2 cancel out. And in order to find the number of molecules of H2O, we have to use Avogadro's number. So we know that each mole H2O contains 6.022 times 10 to the 23 H2O molecules. Now moles and moles cancel out. And from here, we should be able to find the number of molecules of H2O. So this answer here is 1.2 times 10 to the 22nd molecules of H2O. All right, let's look at another example. Here we're looking at a combination reaction of aluminum metal and oxygen gas that produces aluminum oxide. We want to know how many moles of aluminum are produced when 0.5 moles of oxygen reacts. So from moles of O2, we're trying to find moles of aluminum. So we're just doing mole to mole calculation. In that case, we can just use the balancing coefficients. So starting with 0.5 moles of O2, and based on the balance equation, each 3 moles of O2 reacts with 4 moles of aluminum. So mole and mole cancel out. And this would be 0.67 moles of aluminum. Now let's look at examples when we go from mole of a given compound to a mass of another one. So you want to know what mass of hydrogen can be produced when 6 moles of aluminum reacts with hydrochloric acid. So moles of aluminum are given, and we're trying to find mass of H2. So from moles of aluminum, we can't go directly to mass of H2. So our plan should be from converting from moles of aluminum first to moles of hydrogen, And once we have moles of hydrogen, then you want to find the mass of hydrogen. So starting from moles of aluminum, so you have 6 moles of aluminum. We're going to use the balancing coefficients as molar ratios to convert in between moles of aluminum and moles of hydrogen. So based on the balance reaction, each 2 moles of aluminum produces 3 moles of hydrogen gas. So moles of aluminum cancel out. And then to convert to mass of hydrogen gas, we have to use the molar mass of hydrogen. So 1 mole H2 is 2.016 grams of H2. So moles of H2 cancel out, and that gives us the mass of hydrogen gas. So from the reaction of 6 moles of aluminum with enough of hydrochloric acid, you would expect 18 grams of hydrogen gas. Now I want to bring your attentions to the way I'm writing these calculations, the write-up for this type of calculations. Please note that next to each quantity there is a unit and also a chemical formula. This is how I expect you to write this too. So next to each quantity, there is a unit, and then the formula of a compound that it represents. So everything has to be very, very clear. So let's look at this question now. You're looking at a combustion reaction of octane. You want to know how many moles of water are produced when 325 grams of octane are burned. So what's given to us is the mass of octane. And we're trying to find moles of water. So in order to find moles of water, we have to have the moles of octane, because once we have moles of octane, we can do molar ratio. But we're given the mass of octane. So in order to solve this, we're gonna go from the mass of octane, this is 18, to moles of octane. And once we have moles of octane, we use the balancing coefficients as a molar ratio to find moles of H2O. So 325 grams of octane. To convert the mass of octane to moles of octane, we have to use the molar mass of octane. So each mole octane is 114.2 grams of octane. And then to go from moles of octane to moles of water, we have to use the balancing coefficients as the molar ratio. So each 2 moles of octane produces 18 moles of H2O. So let's look at another one. So you're looking at a double displacement reaction of silver nitrate and H2S that gives you silver sulfide and nitric acid. You want to know how many grams of silver nitrate are needed to produce 0.25 moles of silver sulfide. So here, moles of silver sulfide is given to us. So from moles of silver sulfide, we want to find the mass of silver nitrate. So in order to find the mass of silver nitrate, we're going to need to have the moles of silver nitrate. So in order to solve this, we're going to have to find moles of silver nitrate first of all. And once we have moles of silver nitrate, we can find mass of silver nitrate. So we have 0.25 moles of silver sulfide. Based on the balanced reaction, each mole silver sulfide is produced from a reaction of 2 moles of silver nitrate. And now to convert to mass of silver nitrate, we're going to have to use the molar mass of silver nitrate, which is 169.9 grams of silver nitrate. Now mole and mole cancel out. So how many grams of nitric acid are required to produce 8.75 grams of dinitrogen monoxide from the following reaction? So what's given to us is the mass of dinitrogen monoxide. So and we're trying to find the mass of nitric acid. So from mass of dinitrogen monoxide, we want to go to moles of dinitrogen monoxide. And once we find the moles of dinitrogen monoxide, we want to find moles of nitric acid and then mass of nitric acid. So we're given 8.75 grams of dinitrogen monoxide. To convert to moles, we have to use the molar mass of dinitrogen monoxide. So each mole of dinitrogen monoxide is 44.02 grams of dinitrogen monoxide. And now to go from moles of dinitrogen monoxide to nitric acid, we're going to use the balancing coefficients as our conversion factors. So each 1 mole of dinitrogen monoxide is produced from a reaction of 10 mole of nitric acid. And then to convert to mass of nitric acid, we're going to have to use the molar mass of nitric acid. So each mole nitric acid is 63.02 grams of nitric acid. So the answer is 125 grams of nitric acid. How many grams of chromium 3 chloride are required to produce 75.0 grams of silver chloride using the following reaction? So mass of silver chloride is given. And we want to find the mass of chromium 3 chloride. So in order to find the mass of chromium 3 chloride, we need to have moles of chromium 3 chloride. So from mass of silver chloride, we're going to find moles of silver chloride. And then we can find moles of chromium 3 chloride. And then we find the mass of chromium 3 chloride. So in order to convert from mass of silver chloride to moles of silver chloride, we're gonna have to use the molar mass of silver chloride. So each mole silver chloride is 143.3 grams of silver chloride. Now, in order to go from moles of silver chloride to moles of chromium 3 chloride, we're gonna have to look at the balancing coefficients. Each 3 moles of silver chloride is produced from a reaction of 1 mole of chromium 3 chloride. And now to go from moles of chromium 3 chloride to mass of chromium 3 chloride, we use the molar mass of chromium 3 chloride. Which is 27.6 grams of chromium 3 chloride.